So today we are going to talk about balanced three-phase circuit. So let's consider a YY circuit. Where we have a Y connected source like so. And this particular circuit will utilize a neutral. Let's call this terminal B, C, and N, such that we have a voltage VAN, a voltage VBN, and a voltage VCN. And we are going to connect it to a Y connected load. So where this is terminal capital A, terminal capital B, terminal capital C, and terminal capital N respectively. And I'm going to call this impedance here on the A phase ZYA, this impedance here on the B phase of the load ZYB, and this impedance here on the C phase of the load ZYC. Our Y-connected source will be connected to our Y-connected load by a series of transmission lines. So I'm going to draw those guys in the middle. So this will be ZWA. ZWB. I don't know why the screen keeps flashing. ZWC, and finally down here on the neutral, we will have ZN. So here's our system. All right. This circuit will be considered balanced under the following criteria. Criteria number one, the magnitude of the phase voltages at the source are equal. So that would mean the magnitude of VAN would have to be equal to the magnitude of VBN, would have to be equal to the magnitude of VCN. Criteria 2 is that the phase separation between the phase angles at the source is 120 degrees. So assuming a positive phase sequence, that would mean that the angle of voltage Bn is the angle of An minus 120 degrees, and the angle Cn is the angle of An minus 240 degrees. Our load impedances must be equal. Meaning ZYA must be the same as ZYB, must be the same as ZYC. And lastly, our transmission line impedances must be equal. So ZWA needs to be equal to ZWB, which needs to be equal to ZWC. So I want to point out something here. There's a fourth transmission line, the neutral, which has an impedance of Zn. That neutral impedance does not have to match the other transmission line impedances. We'll see why shortly. Okay. So in order to figure out what the consequences of having a balanced three-phase system are, we are going to introduce the concept of a line current today. And we're going to do our analysis here looking at the line current. So a line current is simply the current flowing through a transmission line in a three-phase system. So I'm going to scroll up real quick here to the top and identify my three line currents. Actually, there'll be four since there is a fourth transmission line here for the neutral. So this current flowing from lowercase a to uppercase a, I will denote as IAA. Current flowing through transmission line B from lowercase b to uppercase b is IBB. The current flowing through transmission line C from lowercase c to uppercase c is ICC. And finally, the current flowing through the neutral line from lowercase n to uppercase n will be INN. So those are my four line currents in this system. Typically speaking, though, I don't consider the neutral current to be a line current. And again, we'll discuss why in a second. So for this particular circuit, and really every circuit, every three-phase circuit will have these three line currents, IAA, IBB, and ICC, because we can't have a three-phase system without transmission lines connecting our source to our load. The impedance of those lines might be zero, so that they're just wires, but we'll still have those line currents for any closed three-phase system. Okay. Another thing that I'm going to do in reference to our original circuit here, I can denote this is node capital N, this is node lowercase n. So I've just put capital, instead of having just that terminal, I'm treating as all as one large node. And what I'm going to do for the math here, just so that we have a relatively straightforward means of analyzing this guy, is I'm going to set our source side neutral node as a reference. In a real three-phase system, everything is based off of what we would call a floating potential, meaning that there is no direct connection to ground. But to make our math more simple here, we're just going to assume that that source side neutral is at a potential of 0 volts. Purely mathematically, everything will be measured with respect to that. So if we apply Kirchhoff's current law at our load side neutral, capital N, what we would observe is that IAA plus IBB plus ICC plus INN is equal to 0. Then, using Ohm's law, I want to express these currents in terms of known voltages effectively, okay? So what I'm doing here is effectively I'm saying that that current IAA is leaving that voltage source VAN and flowing to the load side neutral, okay? So that current IAA could then be expressed as VAN minus V capital N divided by the impedance that that current sees, which is ZWA in series with ZYA. And I can do that for my others as well. So using Ohm's law, we would have VAN minus capital N, lowercase n, divided by ZWA plus ZYA. My current IBB would then be VBN minus that same VNN divided by ZWB plus ZYB. My current ICC will be VCN, lowercase n, sorry, minus VNN over ZWC plus ZYC. And then lastly here, I want my voltage, my current flowing through my neutral connection here. So if I look at this guy using the same simple nomenclature, I would have the voltage at node lowercase n with respect to ground, which is just 0, minus V capital N lowercase n, right? So that's just going to be negative V capital N lowercase n. So minus V capital N lowercase n divided by, did I call it Zn or Zwn? Just Zn, okay. Is equal to 0. So if we had a balanced network where ZYA was equal to ZYB was equal to ZYC, I could replace all of those load impedances with a single impedance. I'm going to call it ZY. And if I had a balanced network, I could treat all of those transmission line impedances, ZWA, ZWB, and ZWC, as a single quantity as well, which I'll call ZW. So I can say for a balanced network, this equation becomes VAN minus VNN divided by ZW plus ZY plus VBN minus VNN divided by ZW plus that same ZY plus VCN minus VNN all over ZW plus ZY minus VNN over ZN is equal to 0. And now I'm going to do a small amount of mathematic manipulation here. So I'm going to move all of my uppercase n, lowercase n subscript terms to the left-hand side, okay? So I would have V capital N lowercase n multiplied by 1 over Zn. So that's from my neutral wire term. And then I'm going to have 3 instances of 1 over ZW plus ZY. So 3 over ZW plus ZY. And this will equal to VAN plus VBN plus VCN all over ZW plus ZY. So before I move forward here, does the algebra that I've done there make sense? So I pulled out a common factor of VNN, moved it to the left-hand side, and then so I should see a 1 over Zn from my neutral term, and then a 1 over ZW plus ZY from my A phase, B phase, and C phase, which is why I get 3 of them. All right, so this is what it reduces to if our transmission line and our load impedance is balanced. If our source is balanced, VAN plus VBN plus VCN is equal to VAN plus VAN times 1 angle negative 120 degrees. So that's saying that my B phase is 120 degrees behind my A phase, and then plus VAN times 1 angle negative 240 degrees. So my C phase is 240 degrees behind my A phase. Or VAN multiplied by 1 angle 0 plus 1 angle negative 120 degrees plus 1 angle negative 240 degrees. So I would like you to do me a favor and add those three complex numbers together. One angle 0 plus one angle negative 120 plus one angle negative 240.
Yeah, I don't know.
Okay. So the first thing we would do, let me show you what to do, obvious. Go to menu and go over here to 2 to set it into complex mode.
Okay.
So I think you should be in complex mode right now. So then we do 1. Oh, actually, let me delete that. Shift
Oh,
gives me the angle sign, and then 0 plus 1 shift that guy. Yeah, go for it. Negative 120, and the same with negative 240.
I got 0.
I don't think you did it correctly. Annabelle, what were you saying?
I got 0.
So Annabelle gets 0, and that's the answer I'm looking for. So try again real quick. Okay, so in a balanced source, all the voltages added together equal 0. That's not that hugely revelatory, but what that means is that the right-hand side of our equation up there is 0, right? VAN plus VBN plus VCN over ZW plus ZY is equal to 0. What does that imply about VNN, the voltage drop across our neutral conductor? So
Does it also
what
have to
I'm
equal
saying,
0?
yeah, for some reason you're so terribly quiet, and I think it's my computer, not you. I don't know. So what I'm saying is that if this numerator here is equal to 0, the only way the right-hand side can equal the left-hand side is if VNN is 0 as well, right? This is incredibly important, okay? Because what it means is that for a balanced three-phase system, the voltage drop across the neutral conductor will be exactly 0 volts, regardless of what the impedance of the neutral conductor is. So from this, we can see that our neutral conductor current, INN, which was negative V capital N lowercase n over Zn, must also be 0. So the current flowing through the neutral conductor will always be 0, regardless of what the impedance of the neutral conductor is. So this is a kind of an interesting bit of information here, because our neutral conductor in a balanced system behaves as both a short circuit and an open circuit at the same time. So it's actually just showing you that the impedance of it literally doesn't matter. The impedance of the neutral conductor can be anywhere from 0 ohms to infinity ohms and it still behaves in the exact same way. All right, so our line current IAA which was VAN minus VNN over ZWA plus ZYA in a balanced system just looks like VAN over ZW plus ZY. Our line current IBB VBN minus VNN over ZWB plus ZYB now looks like VBN divided by ZW plus ZY. But we can actually take this one step further and say that it looks like VAN over ZW plus ZY times one angle negative 120 degrees. So we know that since our voltages have 120 degrees of separation, it turns out that our line currents are also going to have 120 degrees of phase separation when we have a balanced system. We could then express ICC going from VCN minus VNN over ZWC plus ZYC to VCN over ZW plus ZY or VAN over ZW plus ZY times one angle negative 240 degrees, right? So for a balanced three-phase system, we can observe one, the voltage drop and current through our neutral conductor Zn is equal to 0. We can directly observe that the line currents have equal magnitudes and are separated by 120 degrees per phase. So as a consequence of the line currents having equal magnitudes and a phase separation of 120 degrees, what can we say about the phase currents through our load? They will have same magnitudes and same separation here, because for this YY system, the line currents and the phase currents represent the exact same quantity. what could we then say, understanding that the phase currents have equal magnitudes and are separated by 120 degrees? What can we say about the phase voltages at the load? They will all have the same magnitudes and be separated by 120 degrees. Absolutely right. Now, this one isn't as obvious, but we can also extrapolate this to our line voltages, both at the source and at the load, okay? So our line voltage is at the load. So let's look at VAB, okay? Let's scroll up here and figure out exactly what that would be. So I think I was doing them in green in class the other day, so I'll do it here. So I have this line voltage at my load VAB. I have a phase voltage VAN, like so, and I have a phase voltage VBN, like so. So I could perform Kirchhoff's voltage law around that loop and find that VAB is equal to VAN minus VBN, or IAN ZY minus IBN ZY. So I could think of this as VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees. When I do VBC, that would be VBN minus VCN if I did KCL around my loop, which would look like VAN times 1 angle negative 120 degrees minus 1 angle negative 240 degrees. So I can see pretty easily that the magnitudes of these guys should be the same because it's always going to wind up just being that voltage VAN multiplied by some combination of complex numbers. So the question here is, this operator, what's the phase angle that it's going to have? So 1 angle 0 minus 1 angle negative, sorry, that should be 120 degrees, I believe is going to look like square root of 3 angle 30. All right. What happens when I have 1 angle negative 120 minus 1 angle negative 240? Right. So there's still exactly 120 degrees of phase separation between the two. And if we did VCA, we would see that it would be VAN square root of 3 angle, gosh, what's negative 210 degrees effectively. So our phase voltages, or excuse me, our line voltages will also have equal magnitudes and are separated by 120 degrees. So that means, let's think about what these implications mean. If we're dealing with the A phase, the B phase, or the C phase, they all have the same magnitudes. So it really doesn't matter which phase we analyze. We analyze only the A phase, we know how the B and C phases, at least from a magnitude perspective, behave. Similarly, we know now that no matter what quantity we're looking at on the B phase, it's always 120 degrees away from the A phase. Similarly, no matter what quantity we're looking at on the C phase, it's always 240 degrees away from what we have on the A phase. So we never really have to analyze the full circuit ever again for a balanced system, okay? So what I'd like to introduce now is what's called the single phase equivalent circuit. And we can do this for any YY system because the voltage drop across our neutral conductor and the current flowing through our neutral conductor will always be zero, regardless of what the impedance of the neutral conductor is. So I can draw three simple circuits, all right? So between transmission line terminal lowercase a and my neutral transmission line terminal lowercase n, I have my voltage source VAN. Between transmission line terminal lowercase a and uppercase a, I have my transmission line impedance ZW. And between transmission line terminal A, capital A, and transmission line terminal capital N, I have my impedance ZY. And now what I'm going to do, and so this is technically different from our original drawing, I am placing a short circuit between lowercase n and capital N. So I am not saying that there is an impedance Zn. And the reason I'm not saying that there is an impedance Zn between those two terminals is because I know that that impedance doesn't do anything. So I don't want to incorrectly assume that if I calculated the current flowing through this loop, that I would have to take into account the contribution of the neutral impedance, because I know that if it's a balanced system, I absolutely do not. So this short circuit is because V capital N lowercase n is equal to 0 for a balanced three-phase system. Okay, so we do not carry that piece of information, whatever the neutral wire impedance was, through our calculations, because it'll actually wind up messing things up. We could draw a similar single phase equivalent circuit for phase B. This would be lowercase b, lowercase n, capital B, ZY, capital N, et cetera. And we could do one for the C phase as well. But we don't ever have to do any of those. If we can do the A phase and understand that the B phase, every quantity in the B phase just lags by 120 degrees, there's no point in ever doing it, right? So we can form the single phase equivalent circuits for the other phases, but there's really no point to doing so. So my question to you guys right now is, do you have the engineering capability to analyze that circuit on the left? I certainly hope so, because it's just a simple single loop circuit, right? It's got a voltage source and two impedances. Doesn't get a whole heck of a, and everything is in series. Doesn't get a whole heck of a lot easier than that. So with that in mind, let's analyze the circuit. Let's talk about the different quantities that we could get just from this. So in your homeworks, I'm typically going to ask you the questions on this entire set of material just using effectively kind of like word problems. But I'll go through how to draw what I'm talking about as well, okay? So I might say something like a positive phase sequence, balanced three-phase Y-connected source supplies power to a balanced Y-connected load. The magnitude of the line voltages is 208 volts RMS. If the load impedance per phase is 36 plus J12 ohms, determine the line currents in the system. You may assume that the angle for the voltage VAN is 0 degrees. Okay, so we have a Y-connected source and we have a Y-connected load. So I'm going to draw a simple YY system, right? So here's my voltage VAN. Here's my voltage VBN. Here's my voltage VCN, which means this is A, B, and C. Over here on my load side, have an impedance of ZY. Same impedance of ZY. Same impedance of ZY. I'm not given any transmission line impedances, so I'm just going to assume that there's 0 in this instance. There is no mention whatsoever of a neutral conductor being included, so I'm not going to draw it. Does not matter if it exists or does not exist, it's still a short circuit to us, okay? So what I'm told is that the magnitude of my line voltages, VAB, is 208 volts RMS. Now, it doesn't say VAB in particular, it could be VBC, VCA, whatever, but the magnitude of all our line voltages are going to be equal because this is a balanced system. So it really doesn't matter if I say it's the A phase, the B phase, or the C phase, if all I know about it is the magnitude. So what that means is that I know that if I have a voltage VAB right here, measured between these transmission line terminals, I know what its magnitude is. I have no idea about its phase angle or anything like that. I know that my load impedance is 36 plus J12 ohms. And I know that the angle of VAN is equal to 0 degrees. So if I wanted to analyze this guy in the easiest possible way, what I would do would be draw a single phase equivalent circuit and then figure out what pieces of information, if any, I am missing, okay? So to be clear here, we're asked to find our line currents. So that would be this guy, IAA, this guy, IBB, and this guy, ICC. They will all have the same magnitude and they will be separated by 120 degrees. So if we find one of them, we've found all 3 of them because we understand how a balanced 3-phase circuits work. All right, so my single phase equivalent circuit is going to look like this. Here's my voltage VAN. This is going to be a short circuit. Here's capital A. Here's my impedance ZY, capital N, lowercase n. Short this guy out. This is my line current, IAA. So we should be able to see fairly trivially, in this case, that IAA is just going to be VAN divided by ZY. So do we have VAN? Pardon? Do we have it? VAB, which isn't VAN, right? VAB is a potential difference between transmission line terminal A and transmission line terminal B. VAN is the potential difference between transmission line terminal A and that neutral node, lowercase n, on the left. So do we have VAN? No, we don't. So we don't know this guy. What about ZY? We got that one guy. Okay. So in order to solve this guy, then we have to think of a methodology that would allow us to solve for that quantity VAN, where we need to know both its magnitude and its phase angle in order to get all of our line currents. Okay. So, do you have any thoughts? Okay, so let's find another equation.
Can we do KVL around that loop?
Can we do KVL? Absolutely correct. So we know that VAB will be equal to VAN minus VBN if we do Kirchhoff's voltage law around this loop. Right, so if we start, we know that VAB is here, so we would see the positive polarity terminal of VAN, and then we would see the negative polarity terminal of VBN, which is why VAB is VAN minus VBN. Make sense? Since we know that this is a balanced three-phase source, because we were told so, we could then say that this becomes VAN times 1 angle 0 degrees minus 1 angle negative 120 degrees. Because we know that VBN is VAN, but shifted by negative 120 degrees, which is going to look like VAN times the square root of 3 angle 30 degrees. Because we did that a couple of minutes ago, effectively, right? So from this, we should be able to figure out that the magnitude of VAN is going to be the magnitude of VAB divided by the square root of 3. Now I want to be clear here. I'm not carrying that angle 30 degrees bit because we know that the angle for VAN is 0. We were given that, right? So I'm strictly dealing with the magnitudes here. So does the math that I've done here make sense? VAB, so VAB, no magnitude, divided by root 3 angle 30 degrees is equal to VAN. The phase angle doesn't change the magnitude in any way, shape, or form, right? So this should be 208 volts RMS divided by square root of 3. I'm going to call it 120 volts RMS. It's really 120.08, but 80 millivolts doesn't mean a whole heck of a lot to us, okay? The reason why I chose these numbers is this system would be what's called a 120Y/208 system, which is how electricity is distributed to Nethkin Hall. If you went and you opened up a breaker panel here in Nethkin or one across the street in Bogard, at the very top, it would have a plate that says 120Y/208. That's what this means. If we looked at the transformer from a line-to-line perspective that's feeding it, it's giving us 208 volts. But if we look at it from a line-to-neutral perspective, which is what our outlets use, we have 120 volts RMS. So this is a very, very common configuration for power distribution here in the US. All right, so with that, IAA is going to be 120 angle 0 degrees volts RMS divided by 36 plus J12 ohms. So tell me what you get. My calculator's in my bag. If it's in rectangular, bring your calculator over here and I'll show you how to convert it. So, so for that, 36 plus 12, and then the engineering button.
Oh, that's it?
Yep.
Yeah,
And then you get an answer. So square root of 10.
-18.
Yeah, so, and then you would hit the standard to decimal button, 3.162, because of a little bit of rounding here. Yeah. And let me show you something else real quick while you're here. If you wanted to convert this answer to, say, rectangular format, you press the option button while you're in complex mode, and that gives you all those things. So you can do the argument, the complex conjugate, real part, imaginary part, convert it to polar, or press down to convert it to polar, or to convert it to rectangular.
I don't know that option.
Yep. I'm sorry, I forgot to write down the angle, negative 18 point something, right?
Yeah, -18.
4.3 degrees. All right. So what would our line current IBB be?
Would be the same magnitude plus
Minus 120. Because we have a positive phase sequence, it'll be minus 120. So that would be minus, let's see, 138.43 degrees. Sorry, and this should be amps RMS. Amps RMS. ICC would be that same thing, 3.162, but we would subtract 120 degrees from that, giving us negative 258.43 degrees amps RMS. So we've got all three of our line currents, easy peasy. Now that we know those line currents, I would argue that we could easily figure out, I'm not going to bother doing this because it's trivial at this point. The phase voltage VAN, the phase voltage VBN, and the phase voltage VCN. Although technically speaking, that's just going to be the exact same thing as V lowercase an, V lowercase bn, and V lowercase cn, because I don't have any transmission line impedances to worry about. We could also, if we wanted to, determine our line voltages. And I guess I'll do them in pink because I'm running out of colors. Our phase currents as well. Setting up one, sorry, that should be BN. Simple circuit. And figuring out what that voltage was allows us to calculate all of those load quantities extraordinarily trivially. Okay. So let's break stuff. That's what I like to do. What if we had a system that looked like this? A, B, C, A, B, C. We knew, for instance, that VAN was 120 angle 0 degrees. Volts RMS, ZW is equal to 0.1 plus J 0.05 ohms. And ZY was equal to 12 plus J3 ohms. Could we create a single phase equivalent circuit for this guy?
Wouldn't we want to make the load portion be a Y and Y phase instead of delta
Right,
phase?
so what Annabelle was saying was we'd have to figure out a way to make the load look like a Y connected load in order to draw the single phase equivalent circuit for this. That is exactly what we're going to spend the entirety of next class doing, is trying to figure out ways to make all of our 4 different options for 3-phase circuits look like YY circuits. We could, I'm going to call it suffer through this, but I don't think it would really be all that difficult because we laid the groundwork for analyzing circuits regardless of what their configuration is earlier, right? And so what I mean by that, we can kind of look at this guy a little quick right here, right? So my thing will stop freaking out. So it's kind of a preface as to what we're going to be doing in class on Monday. Today's Thursday, right? We could set up, I'm going to call it a system here, but it really doesn't have to be that involved. Like we could identify our different quantities. So for instance, we would have a line current, IAA, a line current, IBB, and a line current, ICC. And a phase current, IAB, a phase current, IBC, and a phase current, ICA, like so. And we could pretty easily see, I hope this is easy for you guys to see, that my line current, IAA, is simply my phase current, IAB, minus my phase current, ICA. Just using Kirchhoff's current law, right? So I have a current of IAA flowing in to that node uppercase A. I have a current of ICA flowing in, and I have a current of IAB flowing out. With a little bit of mathematical manipulation, I get this guy. Since this is a balanced system, we should be able to say that IAA is just IAB, whatever it is, times 1 angle 0 degrees minus 1 angle negative 240 degrees, because we know that our C phase should lag our A phase by 240. We have enough know-how to get there, setting up a system right now. But the transformations that I'm going to show you on Monday will make us not have to brute force it, set up a system. Like realistically, we could do this using mesh analysis just because we know how all the different quantities are supposed to behave, what the interrelationships between the different quantities are. But it would be difficult and tedious. Whereas with the transformations that I'll introduce on Monday, everything looks like that simple single loop circuit. And then we can get pertinent quantities from that and then work our way back out, right? So if we could write a single phase circuit in order to determine these line currents, we could use this relationship to determine our phase currents, and then we could easily determine every voltage and current in our system without ever solving a system of equations, if that makes sense. So that's really what the goal is. We have the capability as electrical engineers to do this, but it would be effectively the same as working our frequency domain circuits in the time domain. Why would we ever want to do it when we know that there's a shortcut that exists that makes the math easier? So that's what our whole next class is going to be about. All right, so thank the two of you for showing up. Do you guys have any questions or anything for me before we get out of here?